In the last video, I was showing you my new clamp meter, which turned out to be quite a nice one. It's Voltcraft VC330, and I found out that it's more or less the same as Unit UT210E. It's just a different color, different type number, and different brand name, but it's basically the same. I was testing it, and as I expected, some of the viewers suggested that I should take a look inside, as I always do in my channel. Come on, it's new, it has a warranty. But anyway, let's take a look in it. And there's also a lot of viewers suggesting that I should have an account on Patreon. So I finally started one last night, and I'm trying to figure out how to use it. And it seems I already have about 2, 3 or 4 patrons, and I really appreciate your support, especially nowadays when most of the people are using ad blockers to disable the advertising in the videos. So thank you for your support, and the link to my Patreon is in the description. But I promise I'm never going to mention it again, because I really hated how some YouTubers are begging for likes, begging for comments, begging for subscribers, begging for support, for money and so on. How they can lower themselves to such a desperate begging. Especially begging for subscribers at the start of the video, when you have no idea what you are subscribing to. This is just ridiculous, that's so annoying. I'm never going to do it. It's just your decision to subscribe, it's just your decision to go to my Patreon, and instead of begging, I'm going to make early videos for my patrons. But now, of course, let's go back to my clamp meter. So let's take a look in it. Let's remove the probes. Here is the battery space, which you have seen yesterday. There are 2 AAA batteries, and here you can see another 2 screws, which I'm going to open. So is it going to come apart? Yes, and there is some sticker on it. Let's remove it, and that's it. So here you can see the internals of it. There is the main chip in it, which luckily is not a black blob, and another 2 chips. A 14-pin chip and an 8-pin chip. There are some discrete transistors, about 7 of them. Some capacitors, an electrolytic capacitor, a tantalum capacitor, some ceramic or multi-layer ceramic capacitors, some resistors. There is an array of capacitors. What is doing so many capacitors? Is it driving the display? Here I can see some PTC thermistors or resettable fuses for protection, and also some metal oxide varistors. It also has some tiny potentiometers for calibration here. There's also some green wire going to the iron core of the clamp. So the core is grounded, or is it using the core as an antenna for the pillow detector, as I call it, or non-contact test or cable detector? I guess the iron core is the antenna for the non-contact test. The main chip is DM1106EN, and this chip is, well, you can see it. And is this the logo of Texas Instruments? And the last one is another chip starting with DM. And is it some EEPROM memory 24C02? So is it 2 kilobyte memory? And the crystal is 3.999 megahertz. Why not 4? Here you can see the marking of the PTC thermistors and the metal oxide varistors, which don't like to be recorded, so let's take a picture of it. So here you can see the picture of it, and it seems that all 3 of those metal oxide varistors are the same. It says 561, so is it 560 volts? So it's probably limiting the voltage at 560 volts, even though this one is up to 600 volts. But maybe they are in series. I'm probably not going to reverse engineer the entire device, but let's try to reverse engineer the input section with the protections. So let's open it further. I'm not sure if I'm going to put it back together, but anyway. Can I take this one out? Okay, let's remove more screws and this cable maybe. So all the screws are out, and this spring, and the board just comes out. Here is the display. Oh, I shouldn't have removed the shiny screws because it's holding the display, not the board in it. But anyway, here's the display with some backlight. It's this LED. And some backlight panel. Just a piece of plastic or plexiglass. It's basically a light guide, spreading the light from this LED on this entire surface. The light comes in here and there is a shiny foil on the edges, so the light doesn't leak out where it shouldn't. There's a white sticker and a rough surface on the plexiglass to diffuse the light. So here is the display, which was connected using a strip of conductive rubber. The black part of it is conductive and there are some conductive traces, but the pitch of the traces in the rubber is several times smaller than the pitch of the contacts on the display and board, which is quite interesting. It's done like this, so it doesn't have to be aligned. So here you can see the display, the board from the other side. The display was here. Here you can see the contacts of the display, the contacts of the buttons, which are here. Here is the rotary switch with sliding contacts and the pads for it on the board. Here's the white LED for backlight and the red LED for the cable detector, and few more capacitors and resistors, and that's it. Here's the clamp, which comes out, and can I open it somehow? There is some metal core in it, iron core, and this part has no electronics in it, and this one should have the Hall sensor in it. Can I open it? It finally comes apart, and it seems that there are two sensors. Two Hall sensors in it, not just one. One Hall sensor is here, and the other one is here. I was expecting just one. And here it says UT210E, which is the type number of the other one. That's amazing. Here you can see the iron core of it, which is made of iron sheets, just like in a transformer. The type number is also here. Now let's try to reverse engineer the input section of it with the protections, because it's the most important part of it for safety, for reliability, and also to make it idiot proof. So I have drawn some schematic, but I'm going to show it later. Now it's completely and thoroughly taken to bits, and the biggest challenge is to put it back together. The screws go back, and as always, I turn it counterclockwise first, until it clicks, to find the original thread, and then screw it back. Otherwise you cut a new one in it and it falls apart very soon. So I have put it back together, and to my great surprise, it works. So here is the schematic of the protections and the input circuitry. The common terminal goes to the circuit ground, and this one splits into 3 directions. One goes to those resistors, 3 times 300 kilo ohms. In total it is 900 kilo ohms, and there are 3 in series to be able to handle high voltages. And this rail has no protection, no PTCs in it, but it's probably protected by the fact that those resistors have very high resistance. At 600 volts, this is gonna pass only about 0.6 or 7 milliamps. Another rail goes via this PTC thermistor, which has about 1.6 kilo ohms at room temperature, and it goes to the switch as well as this one. And here it's protected by metal oxide varistors, which are 560 volts each, but they are always 2 in series, so the total voltage is 1120 volts. Those 2 rails go into the rotary switch, which has about 7 positions and several poles. Those 2 are only connected when the switch is in this position. For resistances, diodes, capacitors, and a conductivity test. In all other positions, those 2 are disconnected. And the last rail also goes via a PTC thermistor, which has about 1.4 kilo ohms at room temperature. And it's also protected by 2 metal oxide varistors in series. And there are also some very high resistance resistors, 4 times 2.5 mega ohms, so in total it is 10 mega ohms. And this goes into the main chip. So it seems like it's using those 2 for resistors, diodes, capacitors, and conductivity test, and this one for voltage. The resistors are 10 mega ohms, which is the common internal resistance of a modern digital voltmeter. When measuring resistances or diodes, it's probably using this rail to pass some current through it, and it's using this rail to monitor the voltage on it, the voltage drop on it. So this rail is protected by the high resistance of those resistors, and I calculated that at 600 volts, those resistors are going to dissipate 0.4 watts total, or 0.13 watts per resistor. This rail has no resistors in series, but it's protected by this PTC thermistor. At room temperature it is 1.6 kilo ohms, so at 600 volts it's passing 360 milliamps. You have to hope the circuitry is able to survive it, but this current is passing for just a very short time, because at this current and this voltage, this PTC thermistor is dissipating 217 watts. It's gonna heat it up very quickly, and its resistance is going to increase very significantly. So this rail is protected by this PTC thermistor, and I hope this circuitry is able to survive 360 milliamps for a short while, and I hope there is some zener to clamp the voltage down. The last rail is protected by this PTC thermistor and also those super high resistance resistors, so it's not a concern. So it's not so bad, it definitely has some protections. But strangely, from the outside it's Voltcraft VC330, but from the inside it's unit UT210E. The boards have UT210E marking on it. So it seems it doesn't matter which one you buy, you always get the same internals. So this is DiagonWild, and see you in my next videos. And as you can see, it still works after my disassembly.